So dear students, now we are going to study our next named reaction, which is Birch reduction. So Birch reduction is basically a reduction reaction and in this reaction there is a arene which is converted into 1,4-cyclohexadiene. Means, let's say we are having a benzene ring and this benzene ring is converted into 1,4-cyclohexadiene. Two hydrogens are attached to different positions. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So 1,4-cyclohexadiene is formed. Birch reduction has another name as well. It is also known as metal ammonia reduction. As you can clearly see, this is a reduction process because two extra hydrogens are being added to the molecule. This reaction, Birch reduction, was identified by Arthur Birch. Now what we do in Birch reduction is that we reduce aromatic ring. We reduce aromatic rings in an amine solvent. Means we are using an amine as a solvent. Particularly we use ammonia most of the time with an alkali metal. There is an alkali metal dissolved in this solvent. For the convenience, we use sodium most of the time and a proton source. For proton source, we mainly use alcohol, ROH. So there are three key ingredients which are required to perform the Birch reduction. Number one is a metal, sodium. Number two, an amine solvent, NH3. And number third is alcohol, which acts as a protein source. So these three things are required when you perform Birch reduction. So let's say we are converting a benzene ring to 1,4-cyclohexadiene. Okay, in presence of sodium, ammonia and alcohol. So this benzene gets converted into 1,4-cyclohexadiene. Okay, let us take one more example which signifies Birch reduction. Let's say we are having naphthalene ring. We try to reduce it by using Birch reduction. We are using sodium, then ammonia. The temperature is taken around -78 degrees Celsius. Ethyl alcohol is used as a proton donor. So due to this, a 1,4-cyclohexadiene kind of product is formed. So this is an example of Birch reduction. Now, how does Birch reduction takes place? This is a very interesting process to know. See what happens that when we use sodium, which is Na, and dissolve it in ammonia, NH3, sodium releases its electron and sodium forms a complex with the ammonia. It forms a complex compound. The complex compound can be known as Na, NH3, X, and it releases a electron. Such kind of electron, these are acting as counter ions. They are moving free in the solution. These electrons are released by sodium. These electrons are known as ammoniated electrons. Ammoniated electrons. And due to ammoniated electrons, the solution of this, the reaction, the Birch reduction, appears blue. So these ammoniated electrons are the reagent. These electrons are the reagents which are causing reduction. You can also consider them as nucleophiles. They are bound to this complex, hence they are known as ammoniated electrons. Now, these solvated or ammoniated electrons, they basically give rise to radical anion. And this radical anion is the key intermediate in Birch reduction. So this radical anion is the key intermediate. Okay. So now let us understand how Birch reduction takes place by its mechanism. So now we study the mechanism of Birch reduction. So in Birch reduction, what happens is, let's take an example of a very simple example where benzene ring is converted into cyclohexadiene in the Birch reduction. What's happening here is, at first when ammoniated electron arrives, these pi bonds, they are broken in homolytic manner. Like this. So the pi bonds, they are broken in homolytic fashion. One of this electron, it gets attached to the carbon. Okay, so what is the species that is formed? Due to the breakage, this carbon, it gets a free radical. Also, this carbon and this carbon, due to getting new free radical, they create a double bond. And this carbon also creates a free radical. But as you know that this electron is attacked on this carbon, so there are two extra electrons on this carbon, and that is why this carbon gets a negative charge. So the species over here is a radical anion. Okay. Now you know that wherever there is anion, from the previous reaction you have clearly understood where there is anion, it always attracts proton if available. The oxygen will take the electron and radical anion will accept the proton. And now you can see that a proton is accepted. You must not forget that from the beginning there is always a proton lying here. This extra proton arrives at the first place. Okay. Now again, as you can see, at this position there is a radical, there is a radical. Again, electron from the solution comes and makes it a radical anion. Pardon me for mistake. This OH is actually not a water, this is actually alcohol. As I have previously told that we are using alcohol as a source of proton, so please consider it, make it correct that this proton has arrived from the alcohol which we are using in the reaction. So alcohol is acting as a proton source, and because radical anion always attracts proton, it catches this proton and the oxygen hydrogen bond breaks away. Now in the second process, the electron arrives at the later position, para position, with respect to the first protonated carbon, and it again forms a radical anion. Okay, it again forms a radical anion. Now this radical anion can then again get a proton from an alcohol. Okay, it can get a proton from the alcohol, and finally 1,4-cyclohexadiene is formed. So now you have understood that in Birch reduction we are having constant formation of radical anion over here and over here as well, and in the formation of radical anion followed by protonation, our product is formed. It never happens in Birch reduction that all of the double bonds are reduced. So this is a relatively different mechanism. We are not completely removing the double bonds of benzene ring. Rather than we are attaching two hydrogens in the reaction. Okay, so this is the mechanism of Birch reduction. Now there is one more important and interesting thing that I want to mention, is that if an electron donating group is added to the benzene ring, if this is here, the two new hydrogens will come at ortho position. Means this will be double bond. One hydrogen is already lying here in this position. The another hydrogen that comes will be in the ortho position. So this is the product which is mainly formed. Whereas if you have electron withdrawing group, an electron withdrawing group basically forms, it basically forms the two hydrogen at the adjacent position. So please remember that what happens when a benzene ring is substituted by electron donating or electron withdrawing group, and these two groups will determine the outcome of the product. It will determine the regioselectivity of Birch reduction mechanism. Now let us take two examples, and after that you will easily understand. Let us see that there is an electron donating group, for example methoxy group, attached to the benzene ring. This is actually anisole. So as because this is an electron donating group, the product that will be formed would be like this: CH3. The two new hydrogens that will arrive will be attached at ortho position. Now if let's say we are having C double bond O single bond R group, say single bond CH3 group. This is acetophenone. So when there is acetophenone, you see that the double bond or the protonation is done basically at the first carbon, the carbon bearing the functional group, and this is how the products are formed. So I hope you have understood Birch reduction very well. Now we'll meet on the next video.